In this course, we wrote a lot of code and we tested a lot of code, of course. We always tested it manually by simply clicking around in our web application. In this module here, we'll dive into automated testing. That means we'll write code which will actually test our code. So code that runs to run other code and evaluate the results. This is indeed what this module will be about. We'll dive into what exactly testing is and why we use it. We'll have a look at different kinds of tests, namely unit tests, integration tests, and end-to-end tests. And we'll also explore how we can test both synchronous and asynchronous code, and in general, get a thorough introduction into the world of testing. Now, what is testing and why would we want to test? Now, testing, when you hear it for the first time, sounds pretty obvious, pretty straightforward. We are writing an app, we're creating an application, and we simply test it, right? We add a feature, we open the browser, and we test our application. And that is indeed how you will continue to work, even if you do add this kind of testing I'll dive in this video. So testing manually still is something that makes sense. You want to see your application run. So in the end, the idea always is that we have our code and we have some expected result. So if we write some code and then we go into the browser and test this code, we have some idea of what should happen. We want to open that modal, we want to add that user when we click that button, something like this. So we have our expected results in mind, and then we simply test our application. And if we are successful, we are fine with that. We can continue with writing the next piece of code. And if we're not happy with the result, well, then we can modify our code and fix the issue or adjust it such that it works in the way we want. Now, the idea of JavaScript testing or code testing, when you read it like this, is that we automate this testing part. So that we automate it so that we don't have to manually test everything in our application. Now, we will probably still test everything manually, but automated tests can be run whenever we change something in code to see if that affects any part of our application without us having to test everything manually again. That is the idea behind automated testing, that we can see breaking changes or issues in our code, maybe introduced by a change in place A in a totally different place of our app, that we can see this instantly. That is one of the major benefits of writing tests. So that is also one answer to the question, why would we want to test? We want to get an error and see the error if we break our code. We want to see that immediately without us testing everything manually. We might still do manual testing, but it's still worth a lot to have a suite of predefined automated tests that we can run to quickly see, did this change break anything? Well, with well-written tests, we'll get the answer right away. We'll also save time if we don't have to test everything manually over and over again. And we are also forced to think about possible issues or bugs when writing our tests. We have to think about, what do we want to test? How do we write a test that makes sense? And I'll dive into that in this video already. We also can integrate it into our build workflow. This is something more advanced, but there I mean that you could have a build workflow where you push a commit, so a git commit to your code repository like GitHub, and then you have a workflow that automatically is triggered where this code is then tested in the cloud on some server, and if the test succeeds, it's maybe deployed automatically. So you can build a very complex deployment chain there, and tests are then an integral part of ensuring that no breaking or invalid code is deployed. So that is also an advantage of tests, or something you can use tests for. We can also break up complex dependencies, and that is also something I'll show in this video. We have to make sure we write code that can be split up, that is modular, because this will make testing easier, and ultimately it will make working with our code easier. And it improves our code therefore. Since we are forced to follow certain patterns or to write code in a certain way, or at least that will make testing easier, we will write better code altogether. So these are a lot of great advantages, but they might still be a bit abstract when you have not written any tests. So let's dive into testing soon, but not before I try to answer one other question, and that is, which types of tests do we have? I'm talking about automated tests, so some code we write that tests our code. So code that tests code. That is a good description of what testing is, or what automated testing is, I guess. And there we have different kinds of tests. We have some tests that test a fully isolated piece of code. Let's say a function that takes some input and returns some output. We can test such a function with a test because it has a clearly defined structure, and we can say for input X and Y, we expect to get output Z. And that would be a so-called unit test because we test a single isolated unit of our application. We also have some tests that test units with some dependencies. So we have no isolated piece of code anymore, but we might have a function that calls another function, let's say. And therefore, the function we're testing depends on the result of another function. And that is called an integration test, because there we're testing more than just a single unit. We test the integration of a feature into another feature, so to say. We also have the full flow, which we can test, or the user interface. So the full application or a part of the full application. And this is a so-called end-to-end or also user interface test. The idea here is really that we do what we could do manually as well in the browser, but that we write kind of an automated script that executes a certain series of steps for us, and then we can check if the result is the result we expected to get. Now, these kinds of tests have a different complexity. Unit tests are relatively easy to write because you have a small unit and you know it's easy to infer what you want to get as a result. The more dependencies you add, the more complex it becomes because it gets harder to differentiate between what exactly is causing an error. Is it a dependency or the function that uses the dependencies? Also, you might have some dependencies that reach out to a server and fetch data. That is also a complexity you have to handle, and I will show you how to handle this in a separate video. And the full user interface test is the most complex one because there you have to define every step that should be executed and cleverly think about what you want to test and what you want to expect there. Now, also due to this complexity, we write tests in a different frequency. We typically have a lot of unit tests because if you test every unit of your application and it works correctly, you can kind of infer that the overall application will also work correctly. So we will have a lot of unit tests. We then have some integration tests to rule out that two individually working units don't work anymore if you combine them. And we have a few UI or end-to-end tests to test some steps or some flows in our application in the browser in an automated way. So these are the kinds of tests. And in this video, I will show you all three already. And with that, I'd say it's enough of the theory. Let's start writing some tests. For this, I prepared a little starting project, which you of course find attached to this video. And you can simply download that, run npm install in the extracted folder to set up all the dependencies I have here. I don't have many dependencies, I only use Webpack. And then we have a very simple application here in app.js, a JavaScript application, front-end JavaScript, where I import some stuff and then have some code to basically set up an event listener to a button and add a user to a list of users when we click that button. I got util.js, which holds the functions I'm importing into app.js. I'm using Node.js module syntax here simply because that's a bit easier to test and doesn't require a complex build workflow setup on which I simply didn't want to focus in this video. But I use Webpack to then bundle this all up and get a main.js file, which is the file we then use. Now what you can do is you can simply double-click index.html. I got no dev server in place here or anything like that, simply to not focus too much on the front-end workflow. And if you did double-click on that file, this is what you'll get. You can enter some data and add a user, and that is all we can do here. So it's a relatively simple app, but that is great for starting with testing because we can easily confirm if our tests make sense. If they do test something, we would test manually as well. So this is the application, and now let's write some tests. Now, for writing tests, we need some tools that help us with creating these tests. What do we need? We typically need three kinds of tools. We need a test runner, which is simply a tool that executes our tests and summarizes the results and gives us some output on the results. We can use something like Mocha there That is a popular test runner. We also have assertion libraries, and there we define our tested logics, our expected outcomes. So these assertion libraries give us tools to define expectations, to define comparisons, conditions we want to check as part of our tests. There, Chai is a common or a popular assertion library, though what we will use is a very popular library for both running tests and asserting, and that is Jest. Jest is relatively new, or at least it was rewritten not that long ago, and it's a very popular library for writing tests because it is both a test runner and an assertion library, and it's really powerful and a lot of fun to work with. For end-to-end, we also sometimes need a headless browser. So basically a browser where we don't have to click manually, but where we can use the browser API, the DOM and so on, without a user interface necessarily, because we'll analyze it in code anyways. And there we can use Puppeteer, which is a very popular solution for that. We need that headless browser mostly for end-to-end testing, whereas the test runner and the assertion library are also needed for that, but also then are the only things we need for unit and integration tests. Now let's start with Jest and with unit tests. And you can simply Google for Jest to find jestjs.io, the official webpage of Jest.js. And there I can only recommend trying that out, getting started, diving into the official docs to learn way more. But of course, I'll also walk you through all the basics in my videos here. So we'll start installing Jest now. And for that, let's switch over to our project. And in there, let's run npm install --save dev Jest, because Jest will be a development dependency of our project, and it will be the tool we use for running our tests and for checking our outcomes, or for writing some conditions, some assertions as it's called. So this will now install, and with it installed, we can write our first test. And I will write my tests for functions defined in util.js. And there, this first function makes up for a great first unit test. It has no other dependencies because it does not call any other function, it does not reach out to the web or anything like that. It simply takes input, 2 arguments, and returns an output. And this would be a great example for a simple unit test we can write. Now, to write a test for this function, you create a separate file into which you'll store your tests. And you typically name that file like the file you're testing, util, and then .spec or .test.js. The name is up to you. Jest will automatically detect files with .test or .spec in them and will run them automatically once you run Jest, which we'll do in a second. So now I have my util test.js file. And now I want to test my generate text function. For that, I first of all need to import it here. I will use destructuring syntax here to require something from util, so from that util file where the code is stored. And then destructuring syntax simply means I pull out some items from the object, which is in the end exported by the util file, and it will pull out the generate text function. So essentially, I import the generate text function into my util test.js file. And by the way, this is the native way of importing in Jest tests. You could think that you can also use like ES6 imports if you had respective exports in your file, of course, something like this. But this will not work. Not only because I'm not using ES6 exports here, that is also a problem, but even if I would use them, this is not a syntax natively supported by Jest. This Node.js-like import syntax is supported by Jest, and therefore I also wrote my code to use Node.js exports because that made it easier to implement Jest. Obviously, you can also make it work with ES modules, like you use it in React or Angular apps, but there you need a more complex build workflow, you need some additional packages, and I did not want to spend a lot of time on the setup, I want to spend time on testing. Therefore, I use this syntax. So now I'm importing generate text in this file. Now we can write our first test. And for that, we can simply write test here. This is a function which is now globally available, or which will be globally available when we run our tests with Jest. So this is a function provided by Jest in the end. And this function allows us to define a single test. Now, we can give that test a name. That's the first argument. Or not really a name, more of a description, you could say. Something like should output name and age. Typically, you kind of define what you want to test in this name or in this description. So which output are you testing for? You try to put that into your description. Ultimately, you can put whichever text you want in here, but it should be kind of descriptive. The second function argument is then an anonymous function which you pass in, which is the function Jest will execute to really run your test. So in this function, you add your testing code, your code that will be executed. And now here, we can generate some text by calling generate text and storing that in a text constant. And there we'll pass in max and 29, let's say. Now, that is also what I tested here manually. Entering max and 29, added a new item with text max and 29 years old. Now I'm effectively testing that part where this text is generated. So not where the whole item is generated, but only this text. Max 29 years old is what I expect as an output of generate text. Because if we have a look at generate text, well then we return a text here where we have the name and then in brackets 29 or whatever the age is, 29 years old. Now, if we have that expectation, we should formulate it here in the test. And we do this with the expect function, which is also provided by Jest. Now, if you would use a different setup with, let's say, Mocha and Jai, then test would be a function defined by your test runner, whereas expect would be a function provided by your assertion library. And most assertion libraries work with the expect function, because tests are pretty descriptive in terms of function names. We write a test, and then we expect something. Now here, we expect that text, so we pass the thing we want to look into, we want to compare. We expect text is equal to a specific text. And we do this with a bunch of helper functions that we can now chain on our expectable object here. And there you see we have a lot of functions where we could say we expect text to be not a number, for example, or to be null, or just to be. And then here, as an argument to the to be function, we pass the value we expect text to be. That could be a number, but that could be also max 29 years old, which is exactly the output we do expect to get, because it is the output we can also see here. And now with that, we have our first test defined. Now to run this test with the Jest package, I will tweak my package.json file. There we have Jest installed. And we have a script up here, the test script, which is kind of invalid right now. Here, I will just run Jest. And this will automatically search for files with .test or .spec in the name and execute them. Or which end with .test.js or .spec.js, I should say. So now with that added, we can simply run npm test down there in a normal terminal, navigate it into the project folder, and Jest will automatically execute all our testing files. And here we get a beautiful green output. It found one test which passed. And there we see the one test which passed successfully, where it should output name and age, and that succeeded. Now this is great because now, if we ever change something here, let's say we accidentally output the age here too. We change something in that function, in the original function, and we break it. If we save this and then we run our tests again, we now actually get a failed test. And that is exactly where tests can help us a lot. We get a failed test, we see which test failed, should output name and age, and Jest even gives us some information on what failed there. We see that we expected max 29 years old, but we got 29 years old. And this now helps us debug our code and fix our code. Of course, this is kind of a constructed example here, but you could have a typo like this. You could be misusing some variable or some argument. And now if we fix that, we can indeed run this again and get that test passed. By the way, you can also watch with Jest. You can add -- watch here. And now if you run npm test, Jest will actually keep on watching, and you can control the watcher with the shortcuts that are shown there to, for example, force a run of all your tests again or whatever you want to do. And it also means that now, if I do change my file here and I save, just automatically reruns my tests. So this is great, having this run all the time and therefore ensuring that we get errors right as we change something. So that is another great option. And that is our first unit test here. Now this is our first simple unit test. Now before we move on to integration tests, just a quick example for a different kind of test that could also make sense. We should also make sure that it does not just return the valid response here, because we can get this with this trick as well. If I copy the output there, I can also just use return and then this text here. And if I do that, then my first test will always succeed. If I quickly comment out that second snippet. So my test will now always succeed, but I have an error in my function. And we have a second test where we can add a second test where we confirm that this is not the case. So let's say we say should output data less text or whatever you want to name it. And there I could also generate a text with generate text, but I pass an empty string and I pass null as a number here. And then I can expect that text should be, well, what should it be like? It should be basically just a blank and then nothing years old, right? Well, let's give this a try. If I save that, it fails because I always get back max 29 years old because I broke that function. I had a false positive for the first test because I returned the value which I expected there, but the value didn't take the inputs into account. Now I can fix this, of course, and return to the function form I had before. And now the second text will fail because there, whoops, I should expect null years old, of course. I passed null, not nothing. And now there I passed 2 and I have confirmation that I don't have a false positive here. So adding a second test like this might make sense as well to kind of check for the opposite or check the same thing with different arguments, though you could do the same in one and the same test. You can have multiple expects here too. So you could generate Anna 28 here as well. And then simply add another expectation here, text 2, to be Anna, 28 years. And now this should also pass. But having such double checks, that is the main thing, can make a lot of sense to avoid false positives. And here I have a double check as well as testing the opposite. So what happens if I call that function incorrectly? What happens if I pass nothing, for example? Well, then we would expect undefined here, right? And that would be a test that could also make sense. So I'll delete that for now. I'll leave it at this simple unit test, but you should be aware of the fact that you can write multiple unit tests for one and the same thing, then you can check more than one thing in a unit test, and that you might also want to check for false positives or for opposites. But now let's move on to integration tests. So let's now write an integration test. And for integration testing, if we have a look at all our code, which function could we use there? Well, we got the app.js file, we got add user, which uses a lot of other functions, which has a lot of dependencies. So testing this function would be an integration test, but this is a function that does neither take an input nor return an output. Instead, it's a function that really added something in the DOM. So this is something which you might want to test in an end-to-end testing scenario or in a user interface test, but an integration test would be kind of hard here. We would have to do a lot of manual DOM interaction inside of our test, which you can do, but which you might not want to do. Instead, there is something else I can test, and that is basically a part of that function, you could say. In the end, what I'm doing in add user is I do select a couple of elements, then I do validate the input, and then I generate a text based on the input. Now we could outsource this into a separate function, and that is the part of writing modular code that I mentioned earlier. You are forced to write modular code, which also makes your code easier to manage and reuse though. So in util.js, I can export a new function, and let's name it check and generate, or whatever you want to do. Now, check and generate will get a name and an age as an input. And then I will go to my app.js file and I will grab that validation code and move it into check and generate to validate input for, and now that's important, for the name here, and then there for the age, like this. And then if we make it past this if block, I will return a call to generate text where I pass name and age, because that is what I then return here. I return the checked text. So in app.js, where I'm using this, output text is in the end just the result of my call to check and generate. I don't need validate input here anymore. I don't need generate text anymore. I'll just import check and generate, this new function. I'll import that in app.js. And down there, output text is the result of check and generate. And I can move that up here. And here I can now simply check if not output text. So if we did return, let's say, false here, we return false if validation fails. So if this is returned, and therefore if this is not truish, if it is false, for example, then it will return an add user to, and it will not continue creating that element. So now this is the tweaked add user function, and this gives us the check and generate function, which is great to use in an integration test. So let's write a test for it. And I want to test if my validity works correctly, and I then get the expected text back. So it should generate a valid text output, or something like this. And then here in this function, I will test my check and generate function, which I therefore have to import. And I can simply create my text with check and generate, and I pass max and 29 here. And I would expect this text to be equal to max 29 years old. So my expectation actually is the same as in this unit test, but it's not a simple unit test because the function we're testing has more to it. We could fail because validation fails, or because generate text fails. However, generate text is kind of ruled out because we have a separate unit test for this. And this is also how you want to write your tests, by the way. You want to ensure that you drill down like to the smallest possible level and write unit tests for all your units. So write a test for generate text would also be worth writing one for validate input. And then your integration tests really just rely on the units being tested and ensure that the units also work together well. So this is then the idea behind an integration test. So here I have this test, and if I now save this, it actually fails. Now I get an error that validate input is not defined here. And that is true because I do export validate input. I don't need to do that anymore. I should instead create it or define it as a constant. The same is true for generate text so that I can use these functions directly in the util.js file. And then at the bottom, I should also export generate text and assign the generate text constant here, and also export validate input maybe and assign that constant so that I could use it in other files too. And now you see my tests passed. Both tests passed. Now the idea about the integration test is that if I do change something in my check and generate function, for example, here I use my validate input function incorrectly, so the result of that is used incorrectly. Now it fails. And now this is a great example of why I have an integration test. I could have a separate test on validate input, and validate input does work correctly, I can tell you that. But my error is directly here in check and generate. I'm using the result of validate input incorrectly by not checking for it being false, but for it being true. And this means if my name is valid, then I actually return false, which is of course the wrong logic in check and generate. So even though my units work correctly, the combination of the units fails because I have an error here. And this again shows you the power of tests and why integration tests make sense too, and unit tests alone could not be enough, because all units could be working. If you're combining them incorrectly, you still have a problem. So now it's working again though. Now that we had a look at unit tests, what they are, why we use them, and integration tests, let's have a look at end-to-end tests or user interface tests. For this, I'll need to install another tool. So I'll quit my Jest process here, and I will install, with safe dev, Puppeteer, which is a headless version of Chrome, of the Chrome browser. So it basically is a browser we can use to interact with the DOM and so on. We can even run it in a version with the head, so where we see the browser. And we can basically define steps that should be executed in that browser so that we can automate certain processes on our web page and then, of course, test the result of these processes as well. Now, this download will take a while because in the end it downloads the entire Chrome code base because, well, it needs that to be able to simulate that browser. And once it's done, I'll be back. So I'm done installing it. Let's start using Puppeteer now. And for that, I'll go to my util test.js file and I will import Puppeteer. So I'll import Puppeteer by requiring it from Puppeteer like this. And I will write a new test now. And there I will just write should click around for now. We'll fix this later or change this later. And in this function, which should be executed here, I want to use Puppeteer. Now, how can I use it? First of all, I set up a browser by using Puppeteer launch. Now, this will launch a browser with some options which I can define here. For example, I can set headless to false to actually run a browser with a user interface as well. You can set a bunch of stuff here, and you can find it all in the official docs of Puppeteer, of course. I will also set slow-mo here. That will basically slow down the automated operations so that we have a chance of seeing what's happening. And I'll set it to a value of 80. And we can also set some args here, which is an array, where I can pass dash dash and then, for example, window size to launch this browser with these arguments. And window size allows me to set a width height pair. So I can set this to 1920 and 1080, for example. Like this. This should launch a browser with this size. And that, of course, can be great to also test if certain responsive features are working the way you want. So now this will create a browser. Now, actually, this will return a promise. So we can use async await here if we want to by placing async in front of this pair of arguments here, or this empty argument list. And now we can await this to launch. The alternative would be to just use then and catch. Async await in the end does this for you. So here I'm awaiting this and storing the result in browser, you could say. As a next step, I can now create a page object by awaiting the browser to create a new page, like this. Now I also need to tell the browser which page to load, and I'll grab my URL here. And then we can say page, go to, and then you enter your URL, which should be loaded. And you also should await this because all these browser-related things are promises that simply take some time to execute. So you have to await each step. So now this should open a browser and load this page. Let's try this by running npm test. And it should indeed open up a brand new window in Chromium, which is basically like Chrome or the core functionality of Chrome. And you also see that this is being tested, controlled by automated test software. So this was opened automatically. Now let's go back and let's add some logic here. We don't just want to go to that page. Let's say we also want to enter something. For that, I want to enter something into my input with the ID name and age. So in my test, I will await a step where I use that page, where I navigated to my app, where I will then click into the field with that selector. So click takes the selector of the item it should click on. Once I click there, I will type. And again, you can find all commands in the official Puppeteer docs. So you can really instruct the browser, the headless browser, what to do. So I want to type, and I want to type into the same input, and we wouldn't have to click on it first, but I want to simulate all the steps a user would do. And I want to insert, let's say, Anna here to mix it up, not always Max. So now I type in there. I will repeat these steps once I type the name, for the age. So for the age field, I will enter 28, let's say. If you save that, it will open up a new window where you can see that it enters these things. Now we can also add another step and click on this button at the bottom of our page. So in app.js, in the end, it's this button we're listening on for an event. Here with ID button add user, we can grab that selector and make sure we click on that in our setup. And now we get a full flow setup where you see that this gets entered, and then we click this button here at the end. You also saw that it didn't add an item. And this already shows us that writing this text was not the worst idea, because it looks like something was broken. And indeed here in our automated test, if we open the developer tools, we see that it didn't find the validate input function here. So since that was missing or is missing, we have to check our util.js file and see what's wrong with validate input in here. I'm using validate input here, and I'm defining it as a function here. But one thing I never did is I never recompiled my code. That's something we have to do because the code that gets imported in the browser is packed with Webpack, and I never recompiled it after changing my code. So in a separate terminal window, I'll quickly run npm start to get Webpack to run my code. It'll now also watch my code and recompile if I change something. And with that, it should have executed your test automatically. In case it didn't, simply add a blank and reopen your browser and enter, and it will reopen the browser and execute this. And now you see this works. And this is Puppeteer being used for automated testing with a graphical user interface. Now, obviously, we can automate this a bit more and check the result programmatically now to see if we got the expected outcome. Because what I can now do is I can also await, and now that everything executed, I can check if something is the case. For example, I can check for the existence of this list item with a class of user item being added to it. So in my test, I can await my page, and there I can use $eval to get access to an element, and I will look for the first element with a class of user item, and I pass a function as a second argument to eval, where I then define what I want to do with the element I selected there. And here I will get an element as an input, and I will, for example, return the text content. And this means that now the result of this function will be returned by this overall promise, so I can store it here. Final text, for example, will be the text that I fetch from this element that was created. And now I can expect final text to be Anna, 28 years old. Now it's again checking for that text, but it's now using the full flow in the browser. It's not just a unit or integration test as we have it up there. It's really going through all the steps we would execute manually as well. And then, of course, we should have that text, but we could check anything here. We could also check for the existence of this class. And we implicitly do so, because if that class would not be there, we couldn't select the element by it, and therefore final text would certainly not be that text. But now if I save this, it executes all our steps here, and it actually fails here because it basically timed out. That's just a limit set up by Jest to ensure that our tests don't take too long. What we can do for that is the test function actually takes a third argument, and that is the maximum timeout, and we can set this to 10 seconds to 10,000 to increase the time we give our browser to complete its operation so that it doesn't time out. And now you see it finishes successfully because should click around, to which we should assign a better name, does give us the result we want. And here I will now say should create an element with text and correct class, something like this. By the way, we can of course now also set headless to true, disable the slow motion, and not set these arguments. And this will now speed up the testing because now it doesn't have to go through that step in a real browser, it does so behind the scenes. And that's one of the advantages of having a headless browser, that you don't have to watch it execute the steps. But it can be nice to see the steps. You can do both. And now we got a full E2E test or a user interface test in place too. Now we had a basic introduction to testing now, to the core types of tests, but thus far we always tested relatively simple code, synchronous code, where nothing special was happening, where no side effects were involved, like a HTTP request going out when a function is called. Now things like that can cause problems when you're trying to run tests, because your tests will also trigger that code which might send a HTTP request, or which might do something which makes the test take longer, might hit a backend API, or might distort results. So now we'll have a look at what we can do to make our tests simpler and focus on the core things and really only test what matters to us. So for this, again, I prepared a starting project, which you find attached to this lecture here so that you can follow along. And if you start the project by double-clicking the index.html file, you'll see a button there. If you click that button, you will eventually see an all uppercase text being printed here. Now, responsible for that output is this code here. I got a very simple setup here using Webpack. And here I'm getting access to a button in my DOM. I'm adding a listener to print a title. In print title, I call load title, which is this function here. In that function, I reach out to fetch data, which is provided in a different file, also created by me. There, I seem to get some data object, of which I extract the title. I then transform this title to be all uppercase and I return that, hence I can print it here. Now if you have a look in this HTTP file, into this HTTP.js file, here I'm using a third-party package, Axios. So this is not written by me, this is another third-party package. And here in fetch data, I make a GET request to a dummy API. So this is a real API in the web, a real request is made here. This API is not maintained by me, it's just an API we can use for playing around, for testing. And there I get back a response object. Axios gives me such a response object, which happens to have a couple of properties, like the status code, for example, but also the data property, which I'm extracting here. This is essentially what I do. Now let's write some tests. I already installed the Jest package here, and I also already configured my test command here to use Jest. I also have a project where I use Node.js import-export syntax because Jest uses that by default, and just as with my other testing video where I gave you an introduction to testing with Jest, there I explained that Jest uses that syntax, that setting it up to understand a different syntax would be more complex, and I still don't want to do that here because here I want to focus on testing async code. So we got everything set up to write some tests, so let's do that. You learned in that last video that you can create a new file with .test.js at the end to have Jest.js pick it up and execute it automatically. So this will be the testing file for app.js. And let's say we want to test print title. Conveniently, I'm already exporting it here at the bottom. So what can we do? Well, in app.test.js, we can use the test function, which is globally available when we run that file with Jest. There we give it a description, some text, some description of what should be tested here. And there I have should print an uppercase text, for example. I have my arrow function then that should execute, or that contains the testing logic. And in there we define our expectations. Now we could expect uppercase text with the help of some regex magic or anything like that. But here, because we'll change that anyways, I just want to expect this text, because right now I will always get that text for the API endpoint I'm hitting. So I expect, and now I need to import that function, which I want to test. So that will be print title. I'm pulling that out of my exported object in the app.js file. So I expect print title, the result of that function call, to be equal to my all uppercase text here. This is my expectation. We can now run that test by running npm test, and this executes all test.js files. And this actually fails because it fails to execute add event listener of null. Now, the reason for that actually is that app.js contains some code that will always run when this file gets executed, and it does get executed when I import from that file. And it tries to access the DOM here, which just doesn't work in this environment here. The real DOM is not loaded here. So an easy way around that is to take that function and export it into a separate file, maybe a util.js file. This is also something we did in the last video already. Export print title here. And what this allows us to do is it allows us to import something from that file only without executing app.js and therefore without hitting the real DOM. So we can rename that testing file here to util.test.js, and we import print title from ./util. And in app.js, since I removed print title from there, we also need to import print title by requiring it from the ./util file here. And now for that to work, I'll also have to move load title over to util.js because print title depends on that. So let's move load title into that file as well. That means that fetch data also needs to move in there. So from app.js, let's grab the fetch data import and move that to the util.js file. And now with that set up, if we rerun npm test here, now it should be able to run our test here. And it does, but I get an error that essentially it expected a string, but it received undefined. And now this already shows us a problem we have with asynchronous code testing. Well, actually in print title, I am indeed returning nothing. So getting undefined as a result makes perfect sense. But even if I would return something, like for example in here, if I not only log the title, but I also return the title in here, if I do that and I rerun, I will still get that error. I can already say that. The reason for that is that, and that has nothing to do with testing, that's normal JavaScript behavior, return statements inside of callbacks or inside of promise then calls are not executed or are executed, but JavaScript does not wait for them. It does not return this value as a return value for this overall function. Instead, this is the return value of that inner function here. And we're not testing this inner function, we're testing that overall function. So in our case here, one simple solution would be to test load title. Here we return something in the inner function, and we also return something in the main function. We return the whole promise. So chances are that we get back a promise here to which we then can listen, and that might allow us to expect something helpful. So let's change something. Let's export load title here so that we can test it. Let's go to util.test.js, and there I will not expect something like that, but I'll get my title. But instead, I will import load title here, and I will execute load title, and this gives us a promise, so I will add then here, and in there, I know I'll get my title, because that's exactly the way I use it in print title, right? I have load title, and then I get my title. So now I have the exact same usage here in util.test.js, and now here I want to expect something that my title should be equal to that, to that uppercase title I got here. So we can grab that title here, copy it, and that is what I expect as a value. Now if I rerun npm test, it actually passes, because now this test succeeds. So this is better. This is how we could test our asynchronous code, but we still have a problem here. The problem is we're still hitting our API. So here in util.js, I'm using fetch data, and if you remember, we're defining that in the HTTP file, so here, and there we're making a real API request. We typically don't want to do that in testing. We might exceed certain API quotas if we do that. If we're testing post requests, we might even edit something on the API, which we certainly don't want to do as part of testing, certainly not with our production API at least. So hitting the API is typically not something we want to do. There also are other reasons against it. What would we achieve by really making that HTTP request? Do you want to test if your API works correctly? If you're building that API, you should do these tests during the API development, not when working on your front end. These two should be separated. So that is certainly not something you want to test. If the API works or not is not something you test in your front end code. You might test error fallbacks or anything like that, but not if the API works correctly. You also don't want to test if the get method exposed by Axios works correctly. That is a method provided by a third-party package, and we rely on that package doing its job. So we also don't test third-party package functionalities. We want to test our own code. And our own code here, for example, is that we extract data, and that here that we transform this to uppercase and that we pull out the title. Now, to focus on that, we do something which is called mocking. We mock features, which means we replace features we don't want to test with some dummy implementations. And how could this look here? Well, in util test.js, we got load title, and we want to test if that successfully transforms our title to be all uppercase, to be this text. Now, to test this, what we need to do is we need to replace fetch data with a mock. Now, Jest gives us a great way of preventing us from using that fetch data method. We can create a new folder called __ mocks, all lowercase, __ next to the files that contain our raw source code. So in this case, in our root folder. Now, here we can add a http.js file, so the same file name as the file that has the function we want to replace. And now in http.js, we can now do some magic to set up some functions that will replace our real functions when running the tests. For that, I'll copy my code from http.js. I'll get rid of Axios though, because I'll not use that here. I'll still export fetch data though. But in fetch data, I'll simply return a promise which I instantly resolve with promise resolve to an object that has a title property with the text I want to test, which I'll now convert to all lowercase though, so delectus autumn. And now that I'm exporting this here, something interesting will happen. In HTTP.js, I added a console log statement to fetch data to see when we're hitting this API and when we're not. If I now run npm test, we are hitting the API, as you can see here. We have that console log statement from the HTTP file in there. Now we can go to util test.js, and in there, we want to add just mock at the beginning and mock the HTTP.js file like this. You can omit .js though. Now if we run npm test, you see, it also took close to a second because it had to do some magic behind the scenes, but you don't see that console log statement. Because what now happens is, when this test gets executed, when this testing file gets executed, Jest goes ahead and replaces the HTTP file with our mocked file. So all the functions that are exported here are then replacing the functions we are normally exporting in the real HTTP file for our tests only. So for the tests only, we use our mocked functions here, so this dummy fetch data, which gives us back an object that allows the other functions to work fine, but which does not hit the API. Because we don't want to test the API response, and we don't want to test the Axios get method. So we can rely on the API returning us an object that has a title property, and we can rely on the Axios get method giving us an object, a response, which has a data property. So we don't need to test that. We want to test whether our code in the util.js file correctly extracts the title and transforms it. And that is the case, otherwise this test would not have succeeded for our mocked implementation of fetch data, where we return an object with a title that is all lowercase, so not what we test for, lowercase, this text. And therefore, since our test succeeds, we know that our transformation here does work. So this is how we can test async code, or how we can replace code, how we can replace functionalities if we don't wanna, in this case, hit the API. The same would be the case for, let's say, code that accesses the file system. You don't want to do that. Instead, you want to mock such functionalities. You can, by the way, also mock global packages like Axios itself. Instead of mocking our fetch data function, you could create a axios.js file here, and there we could export our own get function here, which we of course have to define. Because remember, in my HTTPS file, I am using the get method of the Axios object. So here I want to export a get method, and that should be a function that takes a URL as an argument, but we don't care about that URL here. What we want to do here is we can return an object, which in this case, since this is faking the response from Axios, so we want to fake whatever get gives us back, and that should be a response object which at least has a data key because we're extracting that. So here in the Axios mock, we want to have a data object which should in turn be an object with the title we want to test. So that lowercase title we define here. So basically we're now mocking a functionality which is one level above the last functionality where we mocked our own function. Now we're using or we're mocking the function this raw function, so this function depends on. So now in the Axios.js mock file, I'm returning an object which has a data key, which has an object as a value, which has a title key, which is the lowercase version of our text. And with that being mocked, we can go to our util test.js file. We can comment out this mocking of our HTTP implementation. So we'll now not use this HTTP file we created a second ago. Jest.js will automatically use mocks of global node modules though. So Axios.js, this mock should be used automatically. We don't have to instruct Jest to do that. And now we can simply run npm test. And here it fails because what I return here is not a promise. And this already proves that this mocked file is being used. Otherwise, it would not have failed. I'm returning an object there, and therefore calling then fails. I, of course, have to return a promise here by using promise resolve, so a promise that eventually yields this object. And once I do that, and therefore my mocked get method provides a promise as the real Axios implementation does, once I do that, it passes again. We see fetching data here because we are now using my original fetch data implementation, but the get method we're using here is not the real one, it's our mocked one. So this one here. Now this is how you can mock certain functionalities to test async code or code in general, which might depend on third-party packages. Now there are other strategies as well. You'll also find the term spies or stubs when you venture deeper into testing, and you can definitely also check out these alternative approaches to learn about alternative strategies for working with async code and third-party libraries. Attached to this lecture, you'll also find additional resources that allow you to dive deeper into these topics and into Jest in general, and learn more about testing and build up on the knowledge you gained here. In this module, we'll have a look at programming paradigms, what this means, and most importantly, 3 important programming paradigms you could use when writing JavaScript code. We'll have a look at procedural, functional, and object-oriented programming, and what that means for you and how code would look like if you followed one of these paradigms. Specifically, as I said, we'll first clarify what exactly programming paradigms are, before we then have a closer look at procedural, functional, and last but not least, object-oriented programming. You already learned the basics you need for all these paradigms throughout this course. Now we'll have a look at what exactly such a paradigm is and when you use which. So what are programming paradigms? That's of course important to understand. In the end, you could say it's just a way of writing code. It's about how you write and organize your code. It's not a syntax feature, it's not a special feature exposed by the browser or anything like this. It's really just how you structure your code and how you reason about your program you're writing, so how your code is organized. And in the end, there are three paradigms you could follow. You have object-oriented programming, you have procedural programming, and you have functional programming. Now, what does this mean? If you're writing your code in an object-oriented style, it means that you organize your data and logic in objects or in classes and then in objects based on those classes, which means you store your data in properties of objects, you store your logic in methods of objects. That's how you typically think about your code here. Everything in your application, in your project, gets represented as a class and then in the end as an object. So you organize your code in logical entities, you could say. You kind of try to translate the application you're writing into the real world, and you think about your application and the things that make up your application in real world terms. If you're building a shop application, you think about products and a shopping cart and so on. That's how you think about your code and how you organize it. Now, when you're following a procedural style, and that's probably the style with which you got started when working with JavaScript, you simply write a sequential series of execution steps and tasks. So you have a top to bottom code execution, you could say. Now, you always have that in every style, but here you simply list these different steps the engine in the end should execute and should perform. You don't organize your code in logical groups or in logical pieces of data. You don't use objects and entities to structure your code. In the end, you just execute step after step. And then we have functional programming, and there we organize our code in, if possible, pure functions with clearly defined tasks. You get all the data a function needs as parameters, and then this function often also returns something new. So you pass data around with parameters, and your functions are your way of organizing your code. You have many functions, probably more than you have in the other styles, and your functions hold your logic. Every function, if possible, works on its own, and this is how you structure your code. Now, that's the theory. It, of course, becomes way clearer if we see that on a real example. So let's work on a very simple example application. And this indeed will be a very trivial application here. It's an application where I in the end have a HTML file which renders a form with two inputs and then with a button, and I got some styling so that this doesn't look super ugly. Now we can simply open this by in the end double clicking that index.html file in the Finder or Windows Explorer. And what we get is something that looks like this. Now here nothing happens. If you enter something here and click the button, you'll just submit the form and therefore reload the page. Besides that, nothing will happen. We will now write code that changes this, and we will write this application code 3 times in the 3 different programming styles. And we'll start with procedural because, as I mentioned, this might be the style you used when you started with JavaScript, because I would argue it is the style that's the most obvious to use if you're getting started with programming. So let's add a new script here, procedural.javascript. You can of course name it however you want. And in the index.html file, below that link here, I'll add a script import and point at procedural.javascript, add the defer attribute to make sure that this script only runs after the entire file has been parsed, and of course close the script tag as well. And now we are importing this and we're ready to write some code. And now we can really think about the different steps we want to execute, because that's what procedural programming is all about. So if we have a look at our HTML file, what do we want to do? Well, we want to listen to a click on this button, of course, or to be precise, we want to listen for the submission of the form. We want to get the values the user entered for the username and for the password. And we might want to validate those values, so at least make sure both fields are not empty, show an error message if they are empty, And then in the end, if everything has been valid, do something with the data. Let's say create a new object, a new user object, and then log that to the console or something like this. So something fairly trivial. That is what we could do here. So for that, back to the procedural JS file, what do we need to do here? Well, we need to get access to the form and to the two inputs so that we can work with the data there. And then we can add a listener to the form and so on. So getting access to those things is easy. We have IDs. We have the user input ID on the form. We have the username ID on this input and the password ID on this input. So we can use these three inputs to gain access. So I'll store the form in a form constant, or I'll store a reference to the form in the form constant. And we can get access with getElementById. And then here it was user-input. And then the second constant I want to create here is the username input. We can get access with document getElementById username. And last but not least, the password. So the password input that can be fetched with document getElementById password, like this. Okay. So we get this access. Let's now add an event listener. So on the form, I'll add an event listener to the submit event because that is the event we want to listen to, right? And then we want to trigger a function when that executes. We could use an anonymous function here, but I will create a named function, the sign up handler, let's say. It will get an event object automatically, and it will point at this function when this event is triggered, when this event is fired. Now this is vanilla JavaScript, and of course, even though we're using the procedural style, we are allowed to work with functions as well. This is not forbidden. We just don't organize our code around the idea of using functions all the time. So we point at this function here when this event is triggered, and now in this function we write all the logic, again, step by step, which we want to execute. So thus far our logic is get access to the different elements, step by step, and then define this function, and then set up this listener. Now when this function runs, we need to get the inputs here, the values the user entered, we need to validate them, and then create a dummy user object with that data. And actually, first of all, I want to call event prevent default to prevent that browser default of sending the form to a backend server, which in the end leads to a page refresh, which I don't want here. So let's call this as well. And now we can get started. Let's get the concrete values the user entered. So we got the entered username, and we can get this out of username input dot value. We can access dot value here because we know that the element we're selecting here is an input element which will have a value property. Side note, you could actually also only get access to the username input in here if you wanted to, because we really only need the two inputs here inside of this function. So you don't have to do it globally here. In this function, it would also suffice. So maybe let's reorganize our code to do that inside of this function. Maybe even after preventing the default, really right before we need a value. That's not required, but it is a possibility. So we get the entered username. We can also get the entered password, and we get that from the password input.value, of course, just like this. Now with the two values, we can validate them. We could do this with a if check, where we check if the entered username, if we trim it to remove excess white space at the beginning and end, if the length is equal to 0, which means this is an invalid input, it's empty. In this case, we could show an alert to the user and say invalid input, username must not be empty. That's something we could do here. And we also return here, which means we cancel this function execution so that we don't continue in the code. If we make it past this if check, we might still have an invalid input because our password, our entered password, whoops, with a double S here, entered password, that might also be wrong. So we trim this and check if the length is 0, or maybe if it's smaller or equal than 5, because let's say we want a password which has at least 5 characters. If it is too short, we can say invalid input, password must be 6 characters or longer. And again, we thereafter return so that we don't continue with the function execution. If we do continue, we made it past both if checks, and we now know we have a valid input. And that's where we now could create a new user object, simply with an object literal. Again, just like functions are not forbidden here, objects are not forbidden here. It's not like you're only allowed to use objects when you're writing object-oriented code. It's more about how you organize your code. And here it's really a step-by-step execution, and we're using a very simple literal object here to store some data, to group some data. So here we then have, let's say, the username, which is our entered username. We have the password, which is our entered password. Entered password. And with that, we're good. And now we can console log the user and maybe also send a greeting with hi, I am plus user.user name, like this. With that, we had a very basic procedural program. If we now save this and we go back to the browser and reload this page, if I enter Maximilian here and then any password of my choice, which is, let's say, too short actually, I get this error, invalid input, password must be 6 characters or longer. If I don't enter Maximilian here, but I leave this empty, I get this error regarding my username. And if I do have valid inputs in both fields here, you see we're logging the user, we're logging hi, I am Maximilian. Now, as I mentioned, this code here should look fairly straightforward to you. There also is nothing wrong with it, but this would be the simple procedural way of writing your code. You think about the different steps you need to execute, and you then just write them down. And don't get me wrong, code will always be executed from top to bottom, but you could also organize this differently. So let's have a look at the object-oriented programming style next. So we wrote this code here in the procedural style, you could say. Now let's create a new JavaScript file, oop.js, where we will write basically the same logic, but now using an object-oriented style. So for that, in index.html, I'll swap the import for the oop.js file here. Now, how would this look like if we think about this in an object-oriented way? Now, there are certainly different ways of approaching this, but I would like to think about the different entities, the different types of objects we could work with here. We could say our form, for example, is one object. It's one object, which in the end will have 2 inputs, which has this button, and which will have a method, which is triggered when the button is fired. The validation could be organized in its own object as well, in a helper object, which holds validation logic that we could reuse in different parts of the application if we had multiple forms. And the user we create in the end, well, we could create a blueprint for this user as well, a class or a constructor function, which allows us to create user objects, which has a built-in greet method to show this greeting, for example. So here in the object-oriented JavaScript file, I will work with classes. If you were working with an older version of JavaScript, you could of course also work with constructor functions instead. Classes in the end are just syntactic sugar with some extras. And you learn all about that, of course, in my complete guide in the object-oriented and classes course section. So which classes do we need here? Well, we have our form, right? So I'll add a user input form class here. And this should hold everything that is related to my form. I also want to have another class, and the order does not really matter here. I'll just have the form at the bottom because it is the thing I will actually start with, and it will use all the other classes which I'm about to define. So I want to define them first, though technically, as I said, you could also organize this differently. But here, another class we'll need later is the user itself. So not the input form, but for the concrete user object we work with. And then maybe also our validator class here, which holds our validation logic. Now let's start with the user input form though. What could be in there? Well, I want to define my constructor function, which allows us to do some initialization work whenever we create an instance based on this class. Now my goal is to create an instance based on this class when the app starts in the end. So therefore here I want to get access to the different inputs in the HTML file and to the form itself so that we can add a listener. So here I will add some properties to the instance created based on the class with the this keyword. For example, a form property, and the name is up to you. And here I get access to get element by ID, user-input. So here I store access to this user input form. I also want to get access to the different input fields in the form. So I have my username input field, document get element by ID, username, and of course one for the password. So password input with document get element by ID, password. So basically, what we stored in constants before, here, this constant, and this constant, is now getting stored in properties of this class, or to be precise, in properties of the concrete objects created based on this class. I also, of course, will reach out to my form and add an event listener here for the submit event. And when this is triggered, I, of course, want to trigger a function. Now, we could work with an anonymous function here, but since we're in a class and we want to write object-oriented code, it makes much more sense to create a method. So a function inside of an object, inside of a class here. So for that, I'll add the signup_handler method here, which gets the event object. And now I can point at it here, this signup_handler. This ensures that this function, which is registered on this class, and which therefore is called a method, is fired whenever this submit event occurs. And in here, we can now do stuff. We can call event prevent default, but we can now also get the concrete entered values and validate them and so on. Now, one important word, if I want to get the, let's say, entered username here, then I, of course, can reach out to this username input. So to this pointer at this input element in the HTML code we stored here, and access.value. But this won't work. Why won't it work? Because the this keyword inside of this method will not refer to this class in this case here. Why? Because this method gets fired upon this event, and when you point at a function or a method based on an event that gets triggered, so here on such an event listener, the this keyword will be bound to the event target. That's a default behavior. To override this, we have to call bind this here. This ensures that the this keyword inside of signup_handler will point to the exact same thing this would point to in the constructor, and that will be the instance created based on the class. So now this will work correctly, and we can therefore also get the entered password here with this password input.value. So now we get the two values. Now it would make sense to validate them. And here again, thinking in an object-oriented way, we could outsource this validation logic into a validator class. We don't have to do that. We could write it inline here. We could just copy over this logic here from procedural. But that means that whenever we have some other form in our application, we can only reuse our code by copying it again. And copy and pasting is not something you want to do too often, because that is a bad programming style. You're repeating yourself and you shouldn't do that. So instead, I'll add something here in the validator class. I'll add a static method, validate. This means we can call it without instantiating this class. And there I expect to get a value, and then let's say a flag, and a validator value if you want to. So I'm writing a little bit of a more complex validator here. What does this mean? Well, value should be the value I want to check, so the entered username and entered password. Flag should then allow us to identify which kind of validation we want to perform. And then validator value is basically optional, allowing us to configure the validation. Now, for this to work, I'll add two new static properties here. Required, and I'm writing it all caps to make it clear that this is basically a globally unique value, you could say, and min length here. And these are just identifiers which we can then use. Because my idea now is that I can check if in here, in the validate function, if the flag argument I'm getting, if this is equal to this required, so if we're running some required validation, and if it is, I want to return true or false. I want to return true if the entered value is not empty, and false if it is empty. So I will return value trim length greater 0. If it's not an empty input, this will return true. Otherwise, this will return false. If the flag is, let's say, this min length, then I will return value trim length greater validator value, so this extra argument with which we can configure validation. Why am I doing it like this? Well, simply just to show that now we would have a reusable validate function. Because in the user input form here, in the sign up handler, we can now use this. We can now simply check if validator, so this class I just worked in, dot validate, which we can call like this because it's a static method, hence we don't need to instantiate the class. If this yields true for the entered username, which is the value, and validator dot required as a flag. So I want to validate this here with the required validator and check if it's not empty. If this returns true, I'm fine. If it does not return true, indicated by this exclamation mark here, I want to show an error. But this is not the only validation, of course. I also want to check one other validation logic here, one other expression. If not, validator validate for the entered password, for the min length flag and a value of 5 as a minimum length. If this returns not true, or this first one returns not true, in any of these cases, I want to make it into this if block. And here we can now show an alert and say invalid input, username or password is wrong. Password should be at least 6 characters. This is the alert we could show here, and then we want to return here to not continue with this method execution. So the error message, the error handling still happens in this class here, which makes sense because this is the place where I do work with my concrete values. But the logic for checking the input is outsourced in a separate class. Now this is not a must do, but it ensures that we could now reuse this validator in other forms of this application as well. And we might of course have more complex validation logic in there than we currently do. So now with this, we know that after this if check we have valid inputs, and hence we could now create our new user. So for this, let's go to this user class and work on this. Here I want to define how a user should look like and attach any logic to it which it should have. So for example here, let's add a constructor to define some values with which we create a user. Specifically the username and the user password, let's say. And then in here we have this user name, set it equal to uname, and this password, set it equal to upassword here. This would allow us to create a new object with these two properties, but I also want to add some logic. I'll add a greet method here to this user object, where I just say console log, hi, I am plus this username. And with that, we can create a new user based on this class down there, our new user with new user. Here we need the new keyword to construct a new instance of the user class. And we forward our entered username and our entered password here. And thereafter, we can not only log the new user, but also call new user.greet to execute that greet logic. And with all that done, there's just one remaining thing now. Thus far, all the logic lives in the user input form, but this is just a class, right? We need to instantiate it to bring this code to life. So below this here, we can call new user input form like this to create a new instance. We could store it in a constant, but if we don't work with this constant, we also don't have to do that. So here I'm just creating a new instance, and with that, this class here now comes to life. We run this constructor, we set up this event listener, and we're therefore good to go. So now if we go back and we reload this page, if we submit an empty form, we should get an error, and indeed we do. If I enter a valid password here, but I have an empty username, it still gets this error. And if I enter a valid username here, but my password is too short, we still get an error here. If I enter a different password, which is long enough, we do log our user object here and this greeting. So this now works, and it's essentially the same logic as before in the procedural style. The difference is now that we think about our code as different objects working together, and we split our code logically into entities, which can make it easier to reason about your code. It can also help with reusing code, As I mentioned at the example of the validator, because we can use this anywhere in the application, in the procedural style, in the way we're doing it at the moment here, we would have to copy this around to share it. And again, copy and pasting is bad, because if you need to change your logic in one place, you then need to change it in 10 places, or how often you're using it. So that's the object-oriented style. Let's explore the functional programming style now. So last but not least, let's explore the functional programming style. For this, I'll create a new file here, functional.js, and of course import this here in the index.html file, functional. The idea behind functional programming now is that we organize our code around, well, functions. So we can still then reuse and share logic by simply sharing a function, by exporting it and importing it in another file and so on. So how could we split this application here into a functionally written application? It can be hard to think about this if you're relatively new in programming. My personal experience shows that object-oriented programming is relatively easy to pick up because it's close to the real world, so to say. We think in objects, and that's how we think about the real world as well. The procedural style also is not too hard because we execute code step by step, and therefore all we have to do is that we have to think about what we want to do in our application step by step. So what should happen when? And then this code is basically writing itself. Now in the functional world, it's a bit like in the object-oriented world. We think about the different things that make up our application, but the things are now not objects, but instead different logical blocks. Something like a validate function, a function to get access to a DOM element, a function to extract user input, a function to create a new user, a function to greet a user. So basically, we try to split our code into the different logical blocks we have here. So in functional.js, how could we get started? Because maybe that helps us understand how it works. It still starts with us getting access to the form, right? We need access to the form so that we can listen to the form submission. To get access here, we could write a new function, connect form, name is up to you. And by the way, you can write this function in any way you want. In this function declaration style here, you could also write it as a function expression, or of course, you could use an arrow function here if you wanted to. That all works. Here, I'll just write it like this. So connect form just like this without any parameters for now. And in there, I want to get access to my form. And I do so by calling document get element by ID user-input. And thereafter, I will reach out to my form and add a submit event listener here. And then what? Then I want to point at a function that should execute when the form is submitted. So maybe let's add a new function here, the signup handler, which gets this event object, which calls event prevent default. It will also do more than that, but this is something we definitely need to do. And then I pointed it here. This is something we could do, but it's not the perfect way of setting this up. Instead, the idea or the core philosophy you really should embrace when writing functional code is that your functions should be pure and all the data they work with is received as parameters so that your functions are as predictable and reusable as possible. So for this connect form function, this means that we would probably get the form ID as a parameter and also the form submit handler function as a parameter. And then here, instead of pointing at user input here, we would point at form ID, and here we would just say form submit handler. And now this function has code which is totally reusable, which makes no assumptions about what's in your HTML file, it makes no assumption about this ID, and about the name of the function that should handle the submission. Instead, we would call connect form here when our app is initialized, so when this JavaScript file is parsed and executed for the first time. And here I would feed in the concrete values, so user input and a pointer at signup handler. Now, of course, in this simple app, we don't gain much by this, but now we really have a function which is pretty focused, pretty straightforward, pretty easy to understand, and which is also pretty reusable because it's not tied to a specific form in the HTML code. If we had multiple forms which we wanted to connect with submit handlers, we could reuse this function and we could just call it with different arguments. That already is how you should think about code when thinking in a functional programming style. So now we connect this form, we point at the signup handler when the form gets submitted. In the signup handler, we now want to get our user input, and we now also, of course, then want to validate it and create a new user. Now again, we could copy our logic from procedural, right? We could copy this logic here for getting the user input for the moment and paste it in here, and this would work. But we're not really thinking in a functional way. What did I just say about functions? Well, they should be pure and should receive all the input they need as parameters. And here again, I'm hard coding IDs, which are IDs from my HTML document, into the function. Now we could do this, but is this good? Well, it's certainly not bad. Now you might argue that hard coding these IDs into the function is not something you want to do because we got rid of it here. But I would argue that the signup handler is of course a very specific function which indeed can be tied to the HTML file because it really is about this signup form. It's not a general function here like connect form was, which should work with any form. This really should only work with the signing up logic. So that is fine. But we're basically having some code repetition here. Why don't we create a new function here which we name get user input, and here I expect to get my input element ID. And in this function, we then return document get element by ID, to which I forward the input element ID parameter, and then I access dot value here. Now, of course, this only works with input elements, but that's the idea behind this function. So we could add an extra check, which checks if this is an HTML input element, but here I just assume that it always will be one. And now we can rewrite this. We can get rid of this line here, and entered username now simply is get user input for the username ID. And we can get rid of this line, and the entered password now just is get user input for password. And again, we have a reusable function here, and this is now leaner and more focused. So now we got the input. Of course, we want to validate it. So unsurprisingly, we create a new function for this, the validate function. And here we could again follow the logic we set up in the object-oriented part. We can expect a value, a flag, and a validator value here. And then basically copy over the logic from OOP, because object-oriented programming and functional program is not that far apart. It's a bit more than just translating classes to functions, but the idea of organizing logic in methods and in classes is not that far away from the idea of organizing logic in functions. So unsurprisingly, we can copy the logic from the validate method here and add it in the validate function here. Now we just need to replace this required and this min length with just required and min length and add some global constants here. And yes, this is also possible. Not everything has to be inside of a function. Here we want some global flags, some global identifiers, and therefore we can define them just like this in our script here. So now we have that, we have our validate function, and we can now use this validate function here in the signup handler. So here we could now call validate and forward the entered username and so on. And that again would not be wrong, but I want to create yet another new function, maybe here, which I'll name create user. And this is a function that takes the username and the user password, and this should now run the validation. And that's just, of course, one way of doing it, not the only correct one, just one way of doing it. So I want to run validation here, and then if it succeeds, also create my user. So in here, I will now check if not validate for username and the required flag, so if this yields false, or if validate for the user password and the min length flag and a min length of 5. If either of the two yields false, we could throw an alert, but this would be a side effect. Now, what's a side effect? A side effect basically is some logic you execute inside of a function which does something outside of the function, which sends an HTTP request, which changes something in the DOM, or like in this case, which shows an alert. So these are typical side effects. A pure function just receives parameters and then maybe returns something. And for the same parameters, it always returns the same thing. An impure function, which has a side effect, might also do that. It might also return always the same thing, but it also might manipulate something outside of the function. So, like I said, in the DOM or a sender HTTP request. Now, sometimes you can't avoid this, but here I want to have create user as a pure function. So I will not throw my alert here. Instead, I will throw a new error here with an error message of invalid input, and I'll just copy the error message from the OOP file here. So copy that string and throw this here as an error message on this JavaScript error. So here we're not showing an alert, we're really throwing an error, and that will automatically cancel the execution of the remaining function. If this error gets not thrown, so if we make it past this if check, if we do have valid inputs, then I will return a new object, and that is my user with a username, which holds the username value, and with a password, which holds this user password value. So now create user is something we could call here in the sign-up handler. We got our new user by calling create user, and we forward the entered username and the entered password. Now this could fail, however. This would throw an error if we have invalid inputs. So here we can use try catch. And again, we could use try catch in the object-oriented style and in the procedural style as well. Don't get me wrong. But now I think here it's really clean to do it like this. We use try catch and we try to create a new user. But if this fails, I will now show my alert here. And yes, this will now produce a side effect, but we could even outsource this into a separate function. Show alert. But since I would do nothing else in there but call the alert function, I'll do it just in here. And as I said, sometimes you can't avoid it. It's okay to have functions that produce side effects. You just want to keep most functions pure and side effect free. Here, however, I will output the error message in an alert. If this succeeds, however, I want to console log the new user and of course also greet the new user. And for that, we could create a new function here, the greet user function, which gets a user object and just calls console log hi I am plus username. And again, this here would also technically be a side effect, by the way, because we do something outside of the function. So here I can then call greet user and forward the new user. And there are different ways of writing this. These are just examples, of course. If we now save this and we reload this page, if the form is empty and I click submit, I get this error. If I have a valid username but my password is too short, I get an error. If my password is long enough but the username is empty, I get an error. And if both is valid and we click create user, we're showing hi I am Maximilian. The log is missing because I didn't enter it here. So here, of course, I want to log my new user and then retry this. So reload. Enter the values here again. And now we get the same output as before. So this now really is working. And now this is an example of functional programming. The core idea, of course, being that we organize our code into functions where most functions are pure and side effect free and therefore highly reusable. So we saw 3 different styles, and of course you can also mix these styles. You could have a procedural style where you also work with classes and where you have multiple functions. You can have a functional style where you somehow also sneak in some classes, though it then technically wouldn't be a pure functional style anymore. Which style is the best though? Well, the best style is the style which best works for you. That really is the truth. Now, there will be people who strongly disagree because, like a couple of other things in programming, this really is something where you can have religious debates. You can really discuss this, and for a lot of people, it seems to be the most important thing in life. Not to me, though. You can write code, you can write apps with either style, and you should find the style that best suits your needs. Now, the more experience you get as a developer, the more you will see that for certain application types, some styles tend to work better than other styles. And again, you can find discussions about this on the internet. Some of them are even kind of friendly, which will show different applications and different examples for when to use which style. You also sometimes have programming languages which strongly favor one style over another. For example, C# is a programming language which is heavily object-oriented. JavaScript, on the other hand, is pretty versatile. There you can follow any style. And therefore, sometimes you also are forced into a certain style and sometimes you are not. It's important to be aware of all these styles. And nowadays, at this point of time, the functional style is really having a strong comeback and is super popular. And it does have great advantages. It's quite readable, your code is really nicely organized, it's very straightforward, functions tend to be relatively small if you're using this style correctly, and it also produces highly reusable code. Object-oriented programming was extremely popular a couple of years ago, and it's still far from being not popular, don't get me wrong. And it does have advantages. It's also producing reusable code, and it splits your code into logical pieces. Now, with the classes, you sometimes have a little bit of overhead, which you don't really want though, and sometimes it's easier to split it when following the functional style. The procedural style is not bad at all and great for some simpler scripts. The more complex your application gets, the more complex it might get to work with this style though, because you will naturally end up with at least using some classes or some other functions to make it more readable at some point, because if you only use this style and you write your steps, your code step by step, your code can get harder to organize and to reason about. But again, here also, you can mix in more functions and so on, and therefore also write great applications with the procedural style. I hope that this overview was helpful and that it helps you make decisions about which styles you want, and most importantly, that it helps you understand styles being used in different projects or in different frameworks you work with in your future as a JavaScript developer. This is now an important, a bit more advanced module. Throughout this course, you learned a lot about JavaScript and a lot about the important things that make up the language. Now, if you want to be a developer, no matter if it's JavaScript or something else, you also need to be able to solve more or less complex problems, and therefore you need to be able to work out algorithms and work with data structures. Or, as I also like to put it, you need to be able to think logically and also to find the best solution for a given problem. This is what this module is about, and you could easily create an entire course about data structures and algorithms, as it turns out. And this, of course, is not the goal here, but this will be an introductory module where we dive into this topic quite deeply so that you know how to get started and build up on this to learn all you need to learn about that topic. Now, what specifically is inside this module, though? We'll have a look at the what and why. What exactly are algorithms and data structures, and why do we need them? But then, of course, we'll also learn about them, learn some example algorithms, and also explore how we can compare different solutions against each other. For that, we'll dive into something which is called time complexity and the big O notation. This will help us measure the performance, you could say, of an algorithm, and will help us make the decision on the best algorithm, the best solution for a given problem. Well, and of course, we'll have a look at a couple of examples. We'll build a couple of algorithms together from scratch so that you get a feeling for how this works and how you should think about this to solve common problems there. Well, with that, let's dive right in and understand what exactly algorithms and data structures are and why we need them. So let's start with the what, and there I want to start with algorithm. An algorithm is not that hard to understand. Often in programming, you have a certain problem where you have some inputs and you want to get to a certain output. So let's say you have an array of numbers as an input, 2, 1, 3 in this case. And now let's say our goal here for a given problem for the application we're writing for a part of that application is to find the minimum number in that array. So in this scenario here, that would be the number 1. We want to find that minimum number. Now, how do we get there? Which code do we need to write to get the minimum number out of this array of numbers? That is the algorithm, the sequence of steps we need there to derive this desired output for the given input. So for the algorithm, we expect the input of a certain format, and that format should always be the same. And we know what we want to get as an output, so the minimum number in this case. And then it's up to us to come up with a number of steps that help us get there, that help us find a solution here. That is what we would call an algorithm, that sequence of steps that gives us, for a given input, a certain desired output. And here we also see a data structure in action, by the way. This array is a data structure, of course one that is built into JavaScript and built into most programming languages actually, but still, it is a data structure. It's a piece of data which also follows certain rules. In the case of an array, an ordered list of data where every item has an index, and we can work with that data structure to solve a certain problem. So here we see both important concepts on one simple slide. The data structure is something like an array or an object or also maps and sets, and the algorithm is a sequence of steps to solve a problem. That is what this module is about in the end. Now, why would you care about this? Well, if you're working on more complex projects or more complex programs, you might need more sophisticated data storage solutions or computation logic to solve certain problems. So you simply need to solve certain problems all the time in programming. If you're working on something, no matter how complex it is, you typically have certain problems you need to solve to make sure that your program does what it should do. So to make sure that your application as a whole behaves correctly. And that involves a ton of simple problems where you might not need to think much about it, but even such simple problems would technically be algorithms, of course. But you might also have some more complex issues, more complex tasks you need to solve. And in order to solve them, you need to know how to think logically. You need to be able to solve problems as a programmer. And understanding algorithms and how to derive them and how to compare different solutions against each other, that is therefore a crucial thing as a developer. You need to be able to do that so that you can solve any problem and you can write good code and in the end also get hired. Because being able to solve problems when being provided with them in an interview is something recruiters are looking for. Often in a job interview, you will be presented with a certain problem, so with some input data and a desired output, and you need to describe and derive how to get there. So you need to build and describe an algorithm whilst you're in a job interview. That is a common task, and even if you wouldn't care about the other parts, though you really should try to become a problem solver, but even if you wouldn't care about that, even if you just want to ace job interviews, you need to understand this algorithm thing and how to derive your own algorithms and think about all of that. So this is what this module is about and why you should care. And with that, I'd say, let's dive right in and let's build our first own algorithm, maybe this algorithm here, so that we get a feeling for how that works and which steps it involves. So let's derive an algorithm. Now we have a certain input. In this case, we have an array of numbers, 3, 1, 2. And what's important here, and that of course is simply just something which is the case for this example, this here is an unsorted array. So it's not sorted in an ascending or descending order, it's randomly sorted. You see we have the smallest item here in the middle, so it could be anywhere. And now our goal is to get the minimum number here. So in this case, we would want to get 1 as a result, because that, of course, is the smallest number in this given array. Now the question is, how do we get there? Well, there are actually different approaches we could follow. One approach is that we simply write an algorithm where we loop, with a for loop maybe, through all the items. And in every loop iteration here, we basically check if the item we're currently looking at, so we go through all the items from left to right, if the item we're currently looking at is the smallest item. So for that, before we actually enter the loop for the first time, we save a, let's say, cur_min variable and set this simply to the first item in the array, so in this case to 3. And then in every loop iteration, we check if the next item in the array, so 1, if that is smaller than the current min. So if I is smaller than the current min, and if I is smaller than the current min, then we set current min to I, so to the item we're currently looking at. And then in the next iteration, we'll compare the next item with the new current minimum. And if the next item is not smaller than the current minimum, we skip this part here in the if check. So instead, we then just continue. And if we do all of that, once we're out of that loop here, so once we're after that loop, we will have a current minimum, and then we just return this current minimum. That would be a simple algorithm we could derive here. We go through all the items and we compare them with each other, so to say, and return our derived minimum at the end. Now this here, what I laid out here, is basically my algorithm written in some pseudo code. So this is not actual code, of course, but it is good enough to explain my ideas. Now we will implement it in JavaScript, and the implementation of an algorithm in a concrete programming language is then called the program. So now we're going to write a program for this problem, which basically implements this algorithm to hopefully give us a solution to find the minimum. Now for that, I'm back in a very simple new project with an empty app.js file and an index.html file where I only import this file, and then my config files here. And now here in app.js, I want to basically implement this algorithm. So actually, I will rename this to alg1 minimum, and I will import this here then, of course. So that's alg1 minimum.js, which I import here. And now in alg1 minimum.js, I wanna, well, write this logic I just described. So let's add a function, maybe call it getMin, because that is what we'll do. And in there, we'll get our array of numbers. So I will name the parameter numbers, and I want to return the minimum number. So for this, let's create a new variable, current minimum, and we'll initialize it in a second. And at the end, we'll return the current minimum. And then we could simply have our test array here, or our test numbers, and that would be 3, 1, 2. That's our array. And I want to get the minimum by calling getMin and passing in the test numbers. And then if we console log min, that should be 1, of course, for this provided array. So with that, let's go to our concrete implementation of this algorithm. Now, as I sketched out before, I want to initialize current minimum with the first number I have in my array I get here. So that's simply my assumption, because I have no better assumption initially, that the first number in the array, so the first number I get to know, is my current minimum, because it's the only number I know from the incoming array. So for the moment, it is the smallest number I know from there. Now, of course, theoretically, numbers could be an empty array, so we could check if numbers length, if that is equal to 0, so if it is an empty array. And if that is the case, we could throw an error if we don't want to support this. So we could throw a new error and say should not be an empty array, something like this. That's something we could do. For that, we can also check if not numbers length, which does not just catch the length equals 0 case, but also the case that we have no length at all, so that we didn't even feed in an array. And we can also check one other scenario. We check that numbers length is equal to 1, which means we have exactly one item. Well, if that's the case, we don't need to check anything. Then we can just return numbers and then the first item here, because if it's an array with only one item in there, of course that only one item is the smallest item, right? So these are two special cases we can check up front, and now we can actually implement our concrete algorithm, so the heart of this task here. So we initialize current minimum with the first number we find in the array, and then we need a for loop. A for loop where we go through all the items in the array. So where we have a variable I, and we actually start at a value of 1, not at 0, because I want to start at the second item with index 1 in the array, because the first item is assigned as my current minimum here. And then here I keep on going as long as I is smaller than numbers length, and I increment I by 1. So in the end here, I go through my numbers array as long as, well, I'm within the boundaries of it, and since the index starts at 0, and I want to start at the second element, I start with 1, and then I keep on going as long as I is smaller than my length, because if it would be equal, it would exceed the array, because, as I mentioned, the index starts at 0. So now, for example, if we have this array, which has 3 items, we would set current minimum equal to 3, so to the first element. Then we would go into the loop where we start at index 1, so at this item here, which also has a value of 1, coincidentally here. So we start at this item, and we execute whatever will be in here, and then we'll increment I to 2 because we start at 1. So we look at this item and execute this logic. And now I is 2, the length is 3, so we execute this. But now we thereafter increment I to 3. Now the length of our array is 3, so this condition is no longer true. So we won't make it into here a third time, which is exactly what we want. We don't want to make it there a third time. So we then return our current minimum. Now we just need to update the current minimum in here. And for that we need to check if numbers for the current index, so for I, is smaller than the current minimum we saved. Because if that new number we're looking at for the index I, if that is smaller, then of course I want to update current minimum and set it to numbers I. Otherwise, if it's not smaller, I will just do nothing and continue to the next loop iteration. And then by the end, we should have a current minimum. And that should already be all here. Now, technically, we can now also remove this check up here, because if we take a closer look at our algorithm, we see that we set the current minimum to our first number here, and if we only have one element in the array, we won't make it into this for loop anyways, so this check is a bit redundant, and we can just keep the first check in case we don't get an array. So that could be our final algorithm, and now let's simply try it. I'm importing it in index.html, so let's simply load this page in the browser and reload it, and I get a value of 1 here for every reload, which is exactly what I want. So it seems to work, but let's verify it. Let's also try some other values. Let's say I only have one element, 3. If I now save this, I get 3. Now if I feed in an empty array, I get an error. Should not be an empty array. So that's also good. Now what if I have 1, 5, 1? So if I have a smallest value twice, well, I still get 1 as a result here. Now what if I feed in 10, -5, -5, 100, 99, -2? I get -5, which is the smallest value, of course. So that seems to work. Looks like we found an algorithm that does exactly what we want here. Now, is this the best solution though? Are there other ways of solving this? And how could we then compare these different solutions? Let's try to implement this in another way. For this, I'll add a new function, getMin2. And there I also want to get my numbers, and I also will run this check here and throw an error if it's an invalid input. But now let's see if we can solve this differently. I think our solution here is not that bad, but still, let's see if we could find a different solution. Now, what could be a different solution? Well, an alternative could be that we try to sort this array we're getting. And if we sort it and we know that we have the smallest item at the beginning, then we could just return the first item in the array. We just have to sort it. So we could return sorted numbers, and they are simply the first item if we sort it in an ascending order. So if we have the smallest item first and then the biggest item at the end. Now we just need a sorted numbers variable here, and we now, well, need to do the actual sorting. Now, how can we sort an array? Now, of course, we could do it quickly by calling the sort function, which is built into JavaScript. But actually, let's write our own sorting algorithm, which is also something we can do. Now, how can we sort our numbers here? Well, we can, again, write a for loop here, where we now actually start at index 0, and we keep on going as long as I is smaller than numbers length. And we then increment it. And now inside of that loop, we have another loop, because I want to go through all items in my array, but then for every item, I want to go through all other items in the array and check if there is a smaller item than the one I'm currently looking at. And this will allow me to sort this. So we can add another loop here, where we maybe use j instead of I, because we can't reuse I here, we are already using that. And I set this equal to I plus 1, so that I started the next item after the item we're looking at in this outer loop here. And then we check if j is smaller than numbers length, because this hasn't changed. We still don't want to exceed our array boundaries. And we increment j. Now we just need to do something before we enter this inner loop. We save an outer element here, and I set this to numbers for the index I, so the element I'm currently looking at in the outer loop. And in here we have an inner element in this inner loop, where we simply take numbers for j, so that we have the concrete elements we're comparing, the one in the outer loop and the one in the inner loop. And then we need an if check in here, where we check if the outer element is greater than the inner element. And if it is greater, then we know, okay, in the array we're going through, so in this array, for example, in the first iteration where this would be the outer and this would be the inner element, we know the outer element is bigger than the inner element. We need to swap positions. We need to replace 3 with 1 and 1 with 3. We need to swap these two so that we order this in an ascending way here. So we need to do a swap here by setting numbers for I, so the index of the outer element, equal to the inner element. So we swap the outer element with the inner element. And of course, that also means that we have to set numbers j, so the inner element's position, equal to the outer element. This simply swaps the two elements in the array. So this array for the first iteration would now swap 3 with 1, for example, so that after this swap, we would have 1, 3, and then 2. This would now be our current array for the first iteration. Now we also need to update our outer and inner element references, because they're now wrong. And now we set outer element equal to numbers for I, and inner element equal to numbers for j. Because since we swapped the elements here in their position in the array, we now need to update these variables again to be correct. so that after the swap we, as I just said, had 1, 3, 2, but before these two lines, outer element would of course still be equal to 3, so to our first element, and inner element would still be equal to 1. Well, now we need to update this after the swap so that thereafter outer element is 1 and inner element is 3. That's what we're doing here. And by the way, if this is confusing at any point, you can simply add a console log statement here, and console log numbers I, numbers j, and then outer and inner element to always keep track of what's where. This, however, will be the logic we need to update the numbers we're getting and to make sure that we actually have a sorted list. So what I'll actually do now is I'll get rid of the sorted numbers array because I just used the numbers array we got as an input here to sort it, and hence here I will just return numbers and then the first element here. So now we have a getMin algorithm, which is of course longer if we compare it to the first one, where we simply sort our list and then return the first element, which has to be the smallest element since we sorted the list in an ascending way with this logic here. So let's see if that works. If I try running this with getmin2, so with this new algorithm, let's see if we still get 1. If I reload here, I get 1. Now let's try this differently. Let's say my algorithm, my array here is this one. And let's see if that works. We should get -10 now. That looks good to me. This is -10. So what if I had just one element in there? That also works and gives me that one element. And what if I have an array that looks something like this? Well, still works. So it seems like this also does the trick now. And it gives us the smallest number. Now, which solution is better then? This one or this one? Of course, we have two different approaches here, and that's quite common in programming. Often you can find more than one solution for a given problem. And now we need to compare solutions to find out which one is better. But how should we compare these two solutions? When we have multiple available solutions for a given problem, we of course want to find the best one. And for this, we need to compare the solutions. But how do we compare different algorithms? In the end, it typically comes down to the runtime performance. We wonder how long does an operation take, and of course we want to pick the solution which takes the less amount of time, so which is fastest to execute. Now the problem just is, of course we could use a stopwatch and measure how long our different algorithms take for different inputs, but this would not really be a good idea. It depends way too much on the hardware we're running on, which other processes might be running in the background, and for small data sets, for small amounts of data, there might be a lot of variation. So indeed, we try to measure and express this in a generalized form and not in time units, not in seconds and so on, because that would be really hard to measure. Instead, we use something which is called time complexity. And there you could simply imagine a chart where you have two axes, and one is the time axis and one is the number of items or the size of the input you're feeding into your algorithm. And then you have a certain relation between the number of items you're passing into your algorithm and the time it takes to execute. And this is expressed with something which is called the big O notation, which we write like this. Now that's very abstract, so let me explain what exactly this means, what the big O notation is, and how we could measure this for our two example algorithms. Back to the two algorithms we wrote. How long does this approach take and how long does this solution take? Well, let's start with getmin. How can we find out how long it takes? For this, we in the end start by counting the number of executions of the different parts of our algorithm. So you could say we count how often each line in this function is reached for a given input. Now let's say here our input is 3, 1, 2. So we're feeding in an array of 3 elements. How often will this block execute then? Exactly once. This is not inside of a loop. This is just in the function itself. We call that function once, no matter how big our array is. So this part here executes exactly once. So one execution. And that's true for the entire if statement, so including the code which is inside of the if statement. Of course, this part technically doesn't always execute. This will only execute if this condition is true, but therefore at most it executes once. Sometimes this line will not execute at all. The if statement overall is executed once. So what about this line here? It's also outside of the for loop, so it also only executes once. We have one execution here because this only gets executed once when the function gets called. Well, actually, to be precise, of course, if we would feed in an empty array or not an array at all, so that our first if statement catches this and throws an error, this line and all the other code in this function would not execute at all. So it's not always running once, sometimes it doesn't run at all. But that would be different cases for this algorithm. So in the best case, from a performance perspective, we get invalid data and the algorithm doesn't run once. That of course is great for performance, not so much for our application logic though. We typically look at something which is called the average case though, which simply means, well, on average we expect valid data and therefore on average this line of course will execute once. So that's just important to understand how you work with these if statements. You can't participate which concrete values you get. You don't know the exact data you get. So we simply take the common case, the typical case we would expect. Now the return statement here also is executed once because we only return once in this entire function. So now what about the for loop? Well, of course, the loop itself, so that we dive into it, executes once, but then the code in the loop executes more often. So we could say this gets executed once, this exact line, but now inside of the loop, of course, we run more often. What about this line here? How often do we run this if check? Well, we have 3 items in the array, but we start the loop at item 2. So this loop for an array of 3 items will run twice. Because it doesn't run for the very first item, it starts at the second item. So here we should have 2 executions of this line here. And then in here, this depends. This depends on the concrete data we get. It might never execute if we have an array as an input where the first element is the smallest, because then this condition will never be met. But if we have an array where we have a smaller item after the first element, then this will at least run once. So this here could be anything between 0 to 2 executions in our case here. For this concrete array, we know it would execute once. It would execute once because for the second element, which is the smallest one, this condition would be fulfilled, and therefore we would run it. So we have 1 execution here for our concrete example. Now, in case this is not entirely clear, you can of course also throw in some console log statements, for example here. And there we could log execution 4 and add a couple of other breakpoints, for example, execution init, and then here execution return, and then you could of course simply count this. So here you see execution init runs once, execution return runs once, execution 4 runs twice. That's exactly what I wrote here. 2, 1, 1. So that's all something you can do if you're not sure whether you counted correctly. So here it looks like we did count correctly. Now, overall, we can therefore also express this in mathematical terms, you could say. We can group this into 3 main blocks. The initialization block here, because these lines here all run equally often. Then the part where we're done. And then also the dynamic part here. And of course, it depends on your algorithm how many different blocks of code you can identify. So here I would say we have these 3 main blocks. Initialization, then our loop logic, and then the return statement. So if we want to derive the time, and with that I mean the number of executions, then we could say that we have 3 blocks. We have 1 execution here for this first block, and 1 execution for this last block. And in between, we have 2 executions. And with that, I don't mean the number of lines that get executed, but simply how often these 3 blocks get executed at most here. Now, why am I writing it like this? Because if we take a closer look at this function here, we actually see that this block and this block are executed in a constant way, which means these 2 blocks don't depend on the input size, on the number of items in the array in this example. No matter if we have an array with 3 items or with 1,000,000 items, this will only run once, this part here, and this will also only run once. So this is constant. So we could have C1 and C3 here. So the first and the third block are in the end constant. So we don't care about the concrete values. Now what about this for loop here? Now here the execution depends on the length of the array. It's basically executing n minus 1 amounts of times, you could say. So for an array with 3 elements, this runs twice. For an array with 1,000,000 elements, this would run 990,999 times. Now, since we initialize our current minimum with the first number in the array here, and therefore this also depends a bit on the array, right? This here also accesses our array. We could therefore also simplify this to just n. And we could say this runs n times C2 times. What is C2? C2 is our constant number of executions we have inside of the for loop. This here runs 2 times, but it only runs once per loop iteration, you could say, right? So this if loop is executed twice because the for loop runs twice because we have an array of 3 elements. But this if statement, of course, only runs once per loop iteration. So we have that constant value of 1 inside of the loop. For every loop iteration, this code here happens to run once. So why am I doing it like this? Because what hopefully gets obvious here is that the constants don't really matter to us. It's not interesting whether we have some code that runs exactly once at the beginning and the end, independent from the input size. We want to measure how long this algorithm takes, so how many operations it executes based on the number of items we feed into it. So if here we feed in 1,000,000 items and this line still only executes once, then this line is simply not interesting for us. This does not make the algorithm any better or worse. Instead, what matters to us are the parts in the algorithm that depend on the input size, because that is what will scale up or down. So here we can simplify this to just n in the end, because this loop, you could say, combined with this line, runs n times. If we feed in an array of 3 elements, this here in the end goes through all the items in the array. So it runs 3 times, you could say. Of course, the loop technically runs n minus 1 times, but for a large array of 1,000,000 items, the -1 really is not interesting. So this simply depends linearly on the length of the array. So here we would say we have linear time complexity. And we typically express this in this big O notation, which means we write a big O and then in brackets the input size, so n. So that simply means our algorithm here depends in a linear way on the number of inputs. If we feed in more items, it will take longer, but it grows in a linear way. So feeding in 1,000 elements takes around 1,000 times as long as it takes for 1 item. It does not grow exponentially or slower, it grows at a linear rate. So the more items we feed in, the longer it will take, but it will grow in a linear way. Now let's maybe have a look at the second approach here to see a different example, a different time complexity, and how this notation helps us compare algorithms. So we derived how long this algorithm in the end takes in this big O notation, where we basically only care about the dynamic parts in the algorithm and not about the constant parts. Let's do the same thing for our second solution now. Now again here we have a constant part, that's this if check, it only runs once. And the same for the return statement. Now we learned that we therefore don't have to care about that. Let's instead focus on the loop, because that's the part that really depends on the array length. Now here we see we go through all items in numbers, and then in there we also go through all items in numbers in the end. Yes, we start one item above the first one, so it's not the entire array we go through, but again, n-1. But as I explained before, for large arrays, this -1 won't make a difference. So in the end, we could say, inside the first for loop, so this line, for example, will execute n times. If we feed in an array with 1,000 items, we'll execute this line 1,000 times, because we go through all the items. And then, and that's the thing, inside of this loop, for every item, so for every n time, we go through the array again. So this executes n times as well in the end. We again go through the entire array. But we do this inside of the outer array. So what's our total time this algorithm will then take? What's the time complexity here? Well, the time complexity here in the end is n times n, because we go through the outer array, and then for every item, so n times, we go through the array again. So we have n times n, and therefore this would be big O n squared. So this simply means for one item, we of course only take one operation. If we feed in an array with one item, we take one operation. But if we feed in an array of 1,000 items, we in the end have 1,000 times 1,000 of different operations we have to execute. So 1,000,000. And that of course is a lot. And that's not growing in a linear way, where for 1,000 items it takes 1,000 times as long, but instead that's a quadratic time complexity here. For 1,000 items, it does not take 1,000 times as long, but 1,000,000 times as long. So therefore, if you compare these two algorithms, these two solutions, where we have a linear time complexity and a quadratic time complexity, of course the linear one is better. This will take way less time. This algorithm here grows in a linear time, so for 1,000,000 items, we take 1,000,000 times as long as for one item, whereas this grows in a quadratic way, which means for 1,000,000 items, we'll take 1,000,000 times 1,000,000 times as long as we do for one item. So if we have these two alternatives, and we don't need to sort for any other reason, we should definitely go with this first algorithm here, because it takes less time. It has O(n) instead of O(n) squared. And that's how we compare algorithms and why this big O notation matters to us. Understanding the time complexities and how you can derive time complexities is super important, and it definitely takes some practice. So if you're not fully on board yet, and if you're not sure you can do this for every algorithm you write on your own, that's fine. We'll also see other examples in this module. I want to come back to one important thing here though, and that is that we of course can also have a look at different cases when we derive the execution time or the number of operations that are performed. Let's take this getMin function here, for example. I mentioned that this here in the end has a constant execution time, and so does the return statement. And this loop here is n-1, or for large n's, so for large arrays we get here, it's actually just n, we could say. Now, of course, we also have different cases we can look at though. For example, here we could say we have a best case, which is that we get an array with just one element, or with no element at all. In this case, we have only one operation that is executed, either this if statement, if it's an empty array and we get this error, or simply this line and this line, so two lines that are executed, but they each run only once. And hence, we don't make it into this loop at all. This loop would not execute at all if we have just one element. So that's the best case. Here we could say we actually have not O(n), so we don't have linear time, but O(1), something which is called constant time. Constant time because our function and the code in there will only execute once. There is not a single line in that entire function which would execute more than once for such an array. Of course, we have multiple lines that are running. We have this line and this if check which executes, but they each run only once, not multiple times. So that would be our best case. Our worst case, on the other hand, would be that we have an array with at least 2 elements, like 3 and 1. And of course, the longer it is, the longer it takes, but this is the case already where all our code in the end executes at least once. So this is a case where we end up with O n in the end. No matter if we have 2 elements or 1,000,000 elements, we need to touch every code, and this for loop will also run at least once. It will basically run as often as we have elements in our array. We can also have a look at the cases in our second function here. There, our best case would be that we have an ordered array, so that we get something like this. We would still execute both loops in here, so we still in the end up with quadratic time, but at least this if statement in here does not execute a single time, so these lines will never execute if the array we get is already ordered. So we would have quadratic time nonetheless, but if we have a look at the entire code in detail, it's a bit better than our worst case where also the code in the if statement is executed. Because here our worst case is that we have an array that is sorted in the other direction. That means we execute this code in the if statement as often as possible. If we have a look at a large quantity of items, we still end up with quadratic time though, because the worst part is that the for loops run all the time, and that's the case no matter how it is ordered. But we run even a bit more code than in the best case. We don't see it here in the big O notation because we don't care about these constant parts, but still, it is a bit worse than the best case. But what I just said is important. We don't care about the small details like this code in the if statement. We care about the big things, and that mainly means about loops in our code. We care about the average case, you could say. And that, of course, is the case where we simply don't know what we're getting, where the input is not known in advance. Because that is the standard case we have to care about. Typically, we don't know which input we get. And in that average case, this code in here might maybe run 2 or 3 or 5 times or not at all. We don't know. That's why this average case matters for us, where we actually have the big O notation and where we ignore these constant factors, but instead where we count the big chunks, like the for loops here, which run over and over again. So it's always the average case that matters for us, not the worst case where we have basically the average case plus some extra executions of the if statement, or the best case where we have the average case minus some extra executions. We don't care about that because we can't anticipate it anyways. We care about the average case here, and the average case really is about the big chunks, so the big for loops, for example, and not some if statements where we simply don't know whether they will execute or not. So we don't count this in, we care about the average case. Now, let's practice what we learned and dive into some other algorithms. For this, I'll add a new file, alg-2, and here I want to write an algorithm that allows us to find out if a number is even or odd. So even, odd, JS sounds like a good name to me. And let me import this here. alg2, even, odd, JS is imported. And now in here, the goal is that we have a function is even or odd, which takes a number, so not an array, but a single number, which of course is also something we can do. And I want to call this is even or odd with 10, for example. And for 10, I want to get even as a result. And on the other hand, if I call this with, let's say, 11, I of course want to get odd as a result. That's the goal. So that is the input, 10 and 11. And for this algorithm, the desired output then is even and odd. How can we implement this? Well, for this, we can get a result by dividing our number with the modulus operator by 2. And this will give us the remainder of a division. So for an even number, the remainder will be 0. And for an odd number, the remainder will be not 0. So we can check if result is equal to 0. And if that's the case, we know it's even. So then we can return even here. Whoops, even like this. Else we know we can return odd. So this is how this algorithm could look like. If we now save this, you see I get even, and that was for this line where I passed in 10, and I get odd for the line where I passed in 11. So this algorithm seems to do the trick. Now we could also shorten this a bit and write it in one line if we wanted to, with a ternary expression, where I check number divided by 2 with this modulus operator. If that is truthy, so if that is anything but 0, we return odd. If it is falsy, so if it is 0, we return even. Keep in mind that 0 is treated as a falsy value. So we have to return even here for the 0, for the falsy case. And if we do that and we save this, we would get the same output as before. So that's an algorithm. Which time complexity does this algorithm have? Now you might think that it matters how we implement it, but that's actually not the case. Let's see how many dynamic segments we have. So code where the amount of executions depends on the number we pass in. And here the thing is, no matter if we pass in 1, 10, or 1 million as a number, our code always runs exactly once. There is no loop in there. There is no recursion in there. So there really is no code that would run multiple times, no matter which number we pass in. So actually here, we say that this has a constant time complexity, or maybe let me put it below that function to be in line with the other code files. And a constant time complexity is expressed as big O of 1. So this means the input really does not matter. This always has exactly the same execution time, no matter which number we feed in. Now, one word of caution here though, it's the case for this algorithm, but it's not always the case that an algorithm or a function with exactly one line, as we have it here, has a constant execution time. And I will come back to a case where this would not be the case later. So for now, let's just accept it like this and let's move on. And let's add a new file, alg_free, and there I'll add a array sum algorithm. So I'll name the file array sum and import it here, alg_free array sum.js. And in there, my goal is that I have an array of, let's say, numbers 1, 2, and 3. The numbers don't matter. The order also does not matter. And I want to be able to console log the result of a function call, sum up or whatever you want to call it, where I pass in the array, and this should then give me the sum of the items in the array, so the sum of the numbers in the array here. So here I would want to get back 6 as a result for this example array. So for that, let's add this sum up array here, and let's accept some numbers here. You can of course name the parameter however you want, and let's build a sum. So maybe let's start at 0 here and return the sum in the end, and now we have to do something here. And how do we sum this up? Well, one way would be to again add a loop where we start at I set equal to 0, where we go through the entire array with this exit condition and increment I after each iteration. And then our sum is simply the old sum plus numbers I. So we add the number we're currently looking at for each index here to the sum, and then we return the sum in the end. And therefore now if we save that and we reload, indeed I do get 6 here. And if we try out a different array, let's say with 5 here at the end, then my expectation would be to get 8. If we do this, I do get 8. So this is of course again a fairly trivial algorithm, but let's see, what's its time complexity, because you really need to be able to calculate this. Well, we got two constant parts here. This first one where we initialize the sum and where we return the sum. This executes once, no matter how many items are in the numbers array. Well, and then we got a loop which goes through the entire array, So, of course, since we go through the entire array, this here executes n times. N is the length of our array, and we go through the entire array. So, the time complexity here would be linear, expressed as O n. So the longer our array is, the longer this function will take, and it will grow in a linear way. So 1,000 items in the array take roughly 1,000 times as long as a single item. And with that, you're hopefully getting a feeling for these time complexities. So let me quickly go through some of the most important ones. For example, constant time complexity, which we just saw. Another example for this would be pushing an item to an array. And I will come back to arrays and data structures in the next lecture, by the way. If we push an item onto an array, we append a new item at the end, so the other items are not affected by this, and therefore this also would have a constant time complexity. No matter how many items are in the array in this example here, this operation will always take equally long. And it was the same for our is, even, or odd function. No matter which number we checked, the operation time was always the same. Now we also learned about linear time complexity, expressed with O(n). For example, sum up, which we just created. This here will take a linear amount of time. The more items we feed in, the longer it takes, but it grows in a linear fashion. 1,000 items take 1,000 times longer than a single item. We also learned about quadratic time complexity, where this would not be the case. We express it with O(n squared, and here, for example, we could write our own sort algorithm, which basically uses the sorting logic we wrote a little bit earlier in this module, where we have nested for loops. If we have a for loop in a for loop, we typically have quadratic time complexity. So that means the more items we have, the longer it takes, but this grows exponentially, so to say. So it's not growing in a linear way, but instead at a faster rate. Now, needless to say that, of course, if possible, you want to avoid quadratic time complexity because you'll quickly reach a point where operations take super long or might not be solvable at all. Now, there also is another complexity which we haven't seen thus far, and that would be logarithmic time complexity, expressed with O log n. And here, for example, that would be a so-called binary search algorithm which we could implement. And there, essentially what happens is that the more items we have, the longer it takes, but it does grow at a slow rate, slower than linear time complexity, for example. So for 1,000,000 items, we don't take 1,000,000 times longer than for a single item. Now, this is a time complexity we haven't seen an example for, and there are other time complexities as well. There is a great article, not written by me, but very helpful, which you also find attached in the last lecture of this module, where you learn more about the algorithms and time complexity in general, and where you also see examples for different time complexities. Different algorithms you can check out to see, for example, such a binary search algorithm for logarithmic time, and so on. This is something I would recommend as your next step when you want to dive into this topic deeper, because this is a great place to learn about different algorithms, different time complexities, and how to calculate them and how to think about them. So this is a strong recommendation that you check out this article. Now, with that, however, I want to leave the algorithms for now and instead focus on data structures, because that's also in the title of this module, and thus far we haven't had a closer look at those. So, what's up with data structures? For this, I'll add a new file, data-structures.js, and in there I want to get started with data structures. So let's import them. And for data structures, it's important to understand that data structure is anything that stores data. So a string like this is a data structure, but of course a fairly trivial one where we can't do much with, and which is also already built into JavaScript. An array is a more interesting data structure, also already built into JavaScript, but very important, and of course one we use a lot. The same for an object or maps or sets. These would all be data structures built into JavaScript. Now maybe let's start with the array, and let's say we have an array of ages 30, 29, 54, something like this. With this array, we can of course do things. We can sum it up as we did before here with the sum up algorithm, or we can find the minimum value, something like this. Now it's important to understand that certain operations with data structures also have certain time complexities. For example, if I push a new age onto this array, what would be the time complexity of this action? Now, of course, push is not an algorithm, not a function we created on our own, but still it is a function that does something. And if you want to learn what it does, you can check out MDN or other resources that explain such built-in functions like this one. Well, it's important to understand how push works. When you push something, you have an array, like this one here, and then push adds a new element in this array, and it adds it at the end. So here where I added this blank space, that is where push inserts an item. Now it's also important to understand, and you learned this, that in an array, the elements are ordered and every element has an index that identifies the element. So here we have an index of 0, here we have an index of 1, and here we have an index of 2, right? Now when we push here, we of course create a new index for that newly added item, the index 3 in this case. So what happens when we push? We add a new item at the end, and this item gets a new index. Does this affect the other items? No, not at all. So adding an item at the end of an array with push has actually a constant time complexity, O1, because the other items are not affected. We add one item, we don't affect the other items, we have a constant time complexity. Now that changes if we use unshift. Unshift adds an item at the beginning of an array. So if we take a closer look at this and I copy that here, then we see that what unshift will do is that it adds the item here at the beginning. Now the problem with that is that means all items effectively have to be moved, you could say. They get a new index. So here this new item receives an index of 0. The item which previously had 0, 30, had 0, now receives a new index 1. The item which previously had the index 1, which was the item 29, receives a new index 2, and so on. So here, for unshift, all existing elements are touched. So this actually has a linear time complexity, On. For every new item we add, we have to touch and move all existing items. We have to reassign indexes. So that is, of course, way worse than pushing. It's also something I mentioned earlier in the course already in the arrays section. So unshifting sometimes, of course, is what you want to do, and then you should do it, but you should be aware that it's way more expensive from a performance perspective than pushing an item to the end of the list. What's also important to know and to understand is that, of course, it also costs you something. It takes some time to find an element. For example, if I want to get my age, and let's say I am 30, then of course, if I know that my age is stored in position 1, or here after unshifting, actually at position 2, I can get it by its index. Index 1 here. Index 1 gives me 30. So if I know that I want my age, and my age is the second item in the array, so it has an index of 1, then I can access it like this, and this actually accesses it at constant time complexity, O1. Why is this constant? Because every item has an index, so JavaScript can immediately go to that place in memory and give me that item. It doesn't need to look at all the other items. Now, of course, this changes if we work with a different data structure. So here's a new example. Let's say we actually have an array name popularity. Now what's in there is a bunch of objects. So we have objects, which is another data structure in an array. And there we have an ID, or a username, whatever you want to call it, like let's say Max, and we have a number of usages. Let's say 5 times. And then here we have the username Manu, and that's getting used 6 times. And of course, we could have more and more items. So effectively, we have identifiers, and then we have values for these identifiers. And now we want to get the usages of Manu. So we want to get the number of times the name Manu gets used. So Manu usages could then be name popularity, where we use the built-in find method, which executes a function on every element in the array, looking at that person or whatever we want to name it. And we have to return true if it's the item we're interested in and false if it's not. So here I look for Manu, so I check if person username is equal to Manu. If that's the case, we return true. We stop searching for more. And then this object will be returned by find. So what I get back is an object which has this usages key. And this gives me the usages of the name Manu. So what I'm doing here is I'm looking for the item with a username of Manu, and then I get the usages for this item. That's what I do with this line here. Now, in the best case, Manu is the first item here. So we execute this function, which we pass to find exactly once, because we find Manu right away for the very first item we're looking at. So we have executed this function once, we get the usages, and we basically, in the best case, have constant time complexity, right? The very first item was the one we were looking for. But that's of course not always the case. The worst case is that we have linear time complexity, ON, because Manu is the last item. And the average case, of course, is somewhere in between, but for a large number of items, this in the end also ends up to be linear time complexity, you could say. So on average, we'll have to walk through all the items or close to all the items to find what we get, because the elements are randomly distributed, let's say. We don't know at which position Manu is, and therefore we have linear time complexity because find executes this function on all items in the array. Now, this is a scenario where another data structure might be a better choice. Instead of using an array like this, why don't we use an object or a map? Let's rebuild this in this better way. We have our name map, let's say, and we can use a normal JavaScript object for this. And now the keys here are the usernames, and the values for the keys are the usages. Like this. And now when we want to get Manu's usages, and I'll just name it Manu usages 2 to not clash with this name, then we can simply reach out to the name map and access the key Manu like this. And then this gives us the usages for Manu. Now this is way better because this will be constant time complexity O1. Because the way JavaScript stores objects internally, they are just key value pairs, and for a given key, JavaScript can instantly give us back the value that's stored for the key. So it doesn't have to go through all the key value pairs, just as an array can instantly give you the value for a specific index. An object can instantly give you the value for a specific key. So if we have a scenario like this, using an object might be better than using an array of objects as we have it here, because we go from linear time complexity in the worst case or in the average case to constant time complexity. Now, if we had a key which is not a string, but let's say some other object or anything like this, then of course we could use a real map, and you learned about that in the data structures section earlier in the course. We can create a new map like this, and then simply add our items to this real map, which is capable of using anything as a key, not just strings or numbers, but also other objects and so on. So a real map is already built into JavaScript. And if you had a scenario where you need uniqueness, you could use a set. So you have these different built-in data structures, and for different operations, they offer different performance or different time complexities. You should be aware of that so that you can use the right data structure for the task you're trying to solve. Now, just as before, here I also got an article I can strongly recommend about built-in data structures and also other data structures you could build on your own, where you also see time complexities for different operations, some comments, and then also some examples for these data structures and how to use them with certain operations. Now, important, this article does not just include built-in data structures like the array, it also shows you how to build brand new data structures with the built-in ones, so building up on the built-in ones, of course, that can be better suited for certain operations or certain tasks. This is a bit more advanced, and I will say right away that in many scenarios you will not need these custom-built data structures, but for highly sophisticated or advanced applications, you might need to build your own data structures, which is then optimized for certain tasks to be faster than what you got built in. But that's a next step after you mastered the basics. For now, it is important to understand the different time complexities of different operations, and that therefore it is important to think about what you plan on doing and coming up with the right or with the best solution for the task at hand to have a well-performing solution. So now in this module, you had an introduction to data structures and algorithms, to time complexities, and also saw some example algorithms in action. There is a great GitHub repository besides that article I mentioned earlier, which I would recommend as a source to dive in deeper. You'll of course also find this linked in the last lecture of this module. This is a repository where you see a bunch of data structures you could build on your own, as well as a bunch of algorithms, including a little hint whether they're for beginners or advanced users, that you could implement with JavaScript. You see a bunch of different examples here, and this is a great place for practicing algorithms and for also, of course, practicing for interviews. You'll find some algorithms here, which we also saw in this module, but of course, as you can tell, there are way more you can dive in. Now, for every algorithm, like the knapsack problem, you can dive in to get an explanation of the problem and what you're trying to solve, then a mathematical pseudocode explanation, and then you also find JavaScript files where the concrete algorithm is implemented, so where you can see what you do to solve this problem. Now, this here, by the way, is a rather complex one, which is why it's a lot of code. There, of course, also are easier ones in there, which you also can use to practice JavaScript and algorithms. Now, what you don't see in here at the moment is the big O notation of an algorithm, but that is, of course, something you can derive on your own with the knowledge you gained here and with help of the extra other article I mentioned. And in general, if you're not sure about the time complexity of something and you want to validate your result, you can always search for something like JavaScript and then the algorithm name, time complexity, and you should find discussions and articles that help you understand this algorithm and also its time complexity. So that is something you can also check out, for example here on Stack Overflow, to learn about the opinions of other people, what they write about it, and what the time complexity of this algorithm should be. In this case, for example, time complexity n times logarithm of n. Now, for interviews, it's important that you don't try to learn all these algorithms here by heart, but that you really just learn how to think about algorithms and how to come up with them, so that you get into this problem-solving thinking and you simply can combine the different skills you gathered throughout this course and with the help of other resources as well to solve problems that might be thrown at you in interviews. It's also rarely important to get the right result. Instead, interviewers want to see how you approach the problem, how you think about this, that you know what big O notation is, and how to derive it. And even if you then make a mistake, people can still see that your way of thinking is correct. And that is what matters here in the end. So with these sources and what you learned in this module, you should now be well prepared to dive deeper into algorithms and data structures and ace your next job interviews then.